Thank you all so much for coming. I don't think maybe I've met a few of you, but I've just been meeting so many people. It's like this conference is actually so awesome. It's also so full of positivity too. So it's really, oh, we have a new one. Hello, we're gonna put you in the spot. Hi. um, yeah, so it's just been really great being here, and I'm really excited to talk to you guys about some facial recognition. Um, so before we can begin, you guys can sort of like use your phones if you want, and you guys can get access to the repo. But also, my brother was kind enough to prepare a nice little server for us with the web app online, so you guys can like do a live demo right then and there if that works. If not, you can just do faces.surge.ai. And feel free to be distracted with it while I speak. So this is what the demo app will look like. Right now, it won't have your name. You have to like put it into the database. Right now, it's going to show my name. Honestly, I could probably just pull it up right now, but you know what happens in live demos. They never work until they do. So a little bit about me. So I feel ashamed because I feel like I wanted to join the club, but I'm not a developer, but I want to feel like one. I want to be cool like you guys. Um, so I don't think I can like wear that the laurel. By day I'm a neuroscientist. So I study brains. I put people in like fMRI scanners. You guys know what MRI scanners are? Yeah, so I put them in these big magnets, and then I try to read their minds. What I do though is like I end up developing a lot of machine learning code and sometimes virtual reality environments because I like to study how people's experiences in spaces like this one influence what they remember. Um, but when I'm not thinking about the brain, which happens too much, and unknowingly, just like that Jeopardy song that I was telling you guys earlier, just like keeps repeating. What I like to do also is create films. And I like to create films that are sort of in like the sort of sci-fi kind of space. So I like to like play a little bit with like 3D modeling, a tiny bit of CGI. Also not CGI artist, so don't expect like some magical things from me. But in that space, I also feel like I'm consider myself a bit of a futurist in the sense that since I do a lot of the neuroscience stuff, and then I'm also doing virtual reality, I'm starting to see like there's this huge intersection that's going to happen really soon, where and it's already happened, honestly. Like, how many of you guys have smartwatches? Okay, so a few. Okay, right. So there's a lot of like already physiological information that's being recorded by a company, a private company, and what are the protections that are available for all this physiological data? As someone that puts people in scanners and then I try to use machine learning techniques to sort of predict what they're thinking and then use certain things that I know about what their experience was like to predict what they're going to say, I start worrying about a little bit about how can this be used in a sort of bad way in real time. So if you guys are interested in like this kind of film and this kind of topics and ethics about this, I'd be really happy to talk to you about this as well. So, okay, so we're going to go into like just general sections. The first, I'm just going to go quickly through like facial recognition technology. Then we're going to go through some example system and then an overview of potential cases and then a recap. So it's literally simple as that. So in general, I mean, you guys probably already all know this, you know, facial recognition technology is just a way that we can match like a face to some sort of digital image or a video frame from some face database. Um, it allows us to be, you know, convenient. It allows for identification. We can create security processes just from facial identification. So as I said, security, identification, convenience, personalization. I've seen some really cool work from people that will use this type of technology to do a lot of really interesting art installations. So you'll have like a face recognition system, you can create a bounding box, and then you can say something like, say, add stable diffusion onto that. And you can start changing the face. And maybe there's something about the context that they're in, and maybe there's some message that needs to be sent. There's a lot of stuff that you can do with this. So it's just about a little bit about being creative. So it the facial recognition kind of history spans many decades, and I don't even know the full history because I'm not an expert. But I know there are moments where people were using punch cards systems, But then until the 90s, there was this thing called eigenface, um, which is a very clever way of sort of dimensionally reducing faces into orthogonal features using principal component analysis. But then there was Viola Jones, who was a game changer for face detection, and this technology kind of started becoming available in cameras in the 2000s. But the stuff that we see in the movies, that didn't really happen until recently. And also, if I don't know how many of you have seen you guys remember how movies there was like enhance, enhance, enhance. It's possible now, right? So when we talk about facial recognition, we kind of have to talk a little bit about the pros and some of the cons, right? You all probably, I mean, like it's easy to talk about the pros because they're important, right? If you're going to say you work in the medical field and you have patient records, and maybe these records contain very sensitive information, and you need to make sure that they're protected. Well, we don't really need facial recognition to, protect these records because there's other more simple and more efficient methods. But there might be other situations where you really, really need to enhance security. And so that all makes sense, right? I don't really have to go through that. But then there's the cons. There's the cons. And there's obviously so I'm not from Europe, right? But I noticed that there's a huge asymmetry where the Europe is usually ahead of the game in terms of like privacy protection and all these things, and the U.S. is always like falling behind. So I wanted to actually hear what you guys think about the sort of bias that comes from some of these systems. Are you guys okay with just going to a public space and having a camera be looking at you and maybe doing some sort of checkings of some sort, checking with a database to see something? Are you cool with that? I'm just curious. No? All right. Come on, let's see. Raise of hands who's cool with it. Raise of hands who's not cool with it. Oh, interesting. Interesting. No, no, no. But it happens, yeah, and it's happening all the time. I consent. um, but yeah, so there's issues with this type of technology, but if we know how to use it, we know how to leverage it, we're empowered. So there's basically two types of facial technology, really, or if you want to call it that. It's identification, which is like trying to identify someone you don't know, and then verification, trying to verify someone. So in that case, it's not just about identifying a face and like, oh, okay, there's a human face, we identify these features. Now it's like, oh, across the database, who is this person? So I brought this up in the talk that I gave yesterday. Um, and so I think that this is an interesting difference in sort of the machine learning approach versus just a very, what would be the word? A more discrete, specific approach, right? So when you're coding, right, you might write a line and you know exactly what that line is going to do. You know exactly why you put it there. You debug, crap, all right, that's not the line that I wanted. I need to fix this line. Everything is very specific, right? But with like a lot of machine learning, it's not so specific anymore. It starts getting a little bit blurry. The role of sort of being the artist and writing the code step by step is still there, but it ends up being a bit more curatorial, kind of like the curation of an art exhibit, because it's no longer about, oh, writing this specific line. It's about what kind of architecture do I want? What kind of input data do I want? How do I want to transform that input data so it's more useful for the architecture that I have? And then there's some output. There's some output that I want, some end goal. And I don't go back and like rewrite a line of code trying to get closer to that end code, end point, although there is a little bit of that. It's more of like, okay, there's some neural network or some sort of model that is going to improve itself. And I'm not going to go in there and change the activation of one node in that. And so I think that's an important distinction because we have to like take a step back and sort of observe things from, oh, there's input data. I might have to transform that in some way. There's going to be something that happens in the middle, and then there's going to be some output. What do I want that output to look like? And did I transform the data the right way? And so I don't know how many of you have experience with this, but the best way that I can describe sort of deep learning, and we're not going to go into super detail on this. I'm just going to like doing a sort of a wavy hand overview, is that deep learning is just a really fancy word for a neural network, and they only started calling it deep learning because they added one extra layer. That's it. Like you can have a one, honestly, you can even one layer neural network and they're still going to call it deep learning. So it's just a fancy word. It sounds cool. I like it. But you don't have to have like, so you've probably seen some papers where they have like a bunch of like crazy like nodes and everything's interconnected. That's also a deep network, but this is also a deep neural network. Um, so the way that I like to describe it is like a factory. And I like this analogy because it starts making sense as to why we need so much training data. So you have a factory, you've been given a factory, it has been gifted to you. Maybe you had some choice in the interior design, some of the aesthetics, maybe it's 2 floors, 3 floors. You've decided that before, maybe not. But okay, let's assume that you have some factory, it's given to you. And you have a bunch of factory workers. They are completely untrained. They have no idea how to do anything at all. And then you bring in some material. Let's say maybe some wood, some thing that looks like a wheel, some material. You put it in the factory. You tell the factory workers, "I need you to build this thing," and they're like, "Okay." And they do something random, and they then come out of the factory, and it's out there, and then you're like, "Oh wait, that's not what I wanted. That's not. Go back and like do it again, right?" So now those factory workers are like, "Okay, that's not what you want. Let me try something else," right? But they are completely untrained. So that new thing that they're going to do, it's also going to be crap. And then you're going to go through that process again. It's because they're completely untrained. The nodes in the network have randomly initialized weights, and as the learning process occurs with tons of data, then they start self-organizing. They start figuring out things of how to like do this, how to do that. But it takes a long time. It takes a lot of GPU power. It takes a lot of money. But thankfully, things are changing kind of slowly. We'll see. Oh, but okay. So in this example, we might have like 4 types of inputs. How we choose them depends. That's another thing. Again, curatorial. We might choose different types of inputs. But in this case, we might choose age, cholesterol level, chest pain, resting blood pressure, and we want to predict if someone is going to have heart disease. But we need ground truth for this. We need to know how these parameters in the past with people that have actually had heart disease. We need some ground truth because we need to train it to learn that there is some relationship, some ground truth, and then the factory workers will self-organize. When they receive that material, then they'll know, okay, usually we have this sort of way of managing when their cholesterol level is this high or not. So anyways, that's a super high level way, but I just think it's important to like remember that there's like a lot of like fancy words that are used to like make everybody's a little scared. So in computer vision tasks, we have classification. So that's just literally taking an image and classifying it. We have detection, so it's like locating an object or a series of objects in an image. And then a more recent sort of development that's happening more and more, which is harder to do in the past, was segmentation. So that's not just, it involves classification, but it's literally creating a mask around the image that contains exactly the object that you want to classify. And Meta, I think it was this year or last year, came out with this really great model, Segment Anything, which is really powerful, and it tries to detect almost anything in an image. It's really good. In fact, it might even detect the border of this, and usually in the more simpler model, it would just capture, oh, screen. So the way that we're going to go through this is through this like sort of simple pipeline. And in some, I'm going to go, so this face detection is not really necessary in all models nowadays. But in some models you do need it, so we're going to go through it just because why not also do the bounding box. So basically what happens first is we do some image acquisition. This is, you can get it from like a drive, a live camera, some sort of image, and we do some pre-processing. So in some cases, we might have to like change the contrast. We might have to like change it to black and white. There's some sort of pre-processing that we have to do to prepare it. Again, curatorial. We need to do curational things before we send it back into the factory. Then we have face detection, where we might use a model that will end up drawing bounding boxes around some face. And so that's a model that was literally trained to find faces and put bounding boxes around them in the service of other models. It's like models and models and models and models. And we have facial alignment, also known as landmark detection. So that's going to look into the bounding box and try to find landmarks that describe a face. There's, past research was like, oh, okay, there's ways that we can sort of, okay, there's a certain distance from the eyes or certain ratios. So now there's landmarks. Necessarily, it doesn't matter necessarily how to do the exact measurements, because that's what people would do in the past. Now we just have, well, I'll get to that in a second. But yeah, so landmarks, finding ears, things like that, eyes. Then we have a facial representation. So as I said, we have some input information, but we need to give it to the factory in a way that's more approachable, more understandable. So what we might do is we might turn that into an embedding, some sort of representation. So we might use another model to do that. So we do a bounding box, we get features, we use those features to create an embedding, and then we use that in a model that's able to represent that more simply, and is able to scale. And then at that point, we can do facial verification, where we search through a database, now looking across these embeddings. So in that case, if we're in an embedding world, that means that we can do a lot of really cool operations, like cosine similarity, do some sort of Euclidean distance. There's a lot we can do once we're in this more high dimensional, but still compressed dimensional space. Yeah, and then after facial verification, we can start making some decisions about, oh, is this Tom? Oh, do I want to give you access to this or not? So I don't know how many of you were at some of the talks yesterday. There was one on vector databases, and then another one that also included a little bit of vector databases. So as I said in the example that I just gave, you could have these features, and you could throw them into even if you didn't want to do the embedding thing and throw them into a network that would give you some representational thing, you could still do the ratios and do some similarity metric there. And you might do that by going through a for loop. You have a database full of people, and then you might just iterate through every one and just like do that on your own. But now we have something that kind of does that more efficiently in these things called vector databases. I'm not an expert in these, but I'm really enjoying them because they're incredibly fast. And they come in with the purpose of being able to do vector operations for searching. And one of the talks yesterday was showing how there's a lot of hybrid vector databases that still use the more classic key-based search, but also with some of the semantic search that exists now. And yeah, where was I? Oh yeah. So yeah. So how many of you have played with OpenCV? Oh, okay. One over here. Okay. How many of you have played with Python? Oh, okay. 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 So OpenCV is an incredible library with documentation. As it happens, some of the best libraries somehow have like really confusing documentation. So this is one of those. It's really great. You can do a lot of stuff with it. It already has some pre-trained models, but we're going to use it here to use a camera. So it's as simple as saying CV2, get me the camera, and then what I want is I want the width and the height. Pretty simple, right? We're just grabbing that information from the camera. Then I forget how dehydrating it is to talk. So then we get the face detection. So this is the image acquisition that we were talking about here in the past over here. So we're going to go through each of these steps, just so reminding you guys. Yeah. So then, So then what happens here is that we go through this endless loop, just like a while loop, just keeps going, and that's just capturing the frame as well as it can, as fast as it can, and then we take that frame and we do a little bit of pre-processing. So I said in the past, pre-processing can depend on like what kind of model you're using. In this case, we don't really need to do much. OpenCV is a package that tends to operate with not RGB color order, but BGR, and it's something that I think actually I'm not really sure, but I might be making this up, so fact check. But it might have to do with when OpenCV was being used a lot, there was a lot of camera companies that were using the reverse order for the color information. So then they just stuck with it. So now it's just convention. And it's really annoying because every time you have to, switch to BGR to RGB. So that's the only thing we really have to do for the preprocessing. And then what do we do? Oh, yeah. And then we have to draw the bounding boxes. And then, yeah, And then what we have to do is, for those that don't know, in Python, imshow is another method that allows us to display something to the user. So we just have it display the frame. So another thing, if you want this to be more efficient, you obviously would want the height and width to be a little bit smaller. Obviously, less pixels, less things to worry about. So this is what it would look like. Yeah, literally that turns into this with a little bit more stuff, obviously. um, so the next step is going to be facial alignment. So now we've been able to draw our bounding box. So that was a separate model that was trained to find faces in an image and tell us the pixel coordinates so where we can draw a bounding box. So every time that I move, and you might have seen it with the web demo, it's going to follow you around. Again, the while loop is going at every iteration possible. So facial alignment is like landmark detection, where we have a bunch of different landmarks. And actually, the library that we're using here actually spits out a lot more landmarks. So here you might only see 68. Uh, and there's, oh, actually, here's a question for you guys if you're paying attention. So this is an image, right? And there's a model that was able to detect the bounding box. Now we have another model that's detecting features, landmarks in the face. Why would it be 68 by 2? So it's a matrix of 68 by 2. We have 68 landmarks, and we need their XY. So we need the actual location in pixel space, right? So actually, the model that we're using actually allows us to do a face mesh. So it's a little bit more complicated, and then actually gives us a Z value as well. But we don't really need that. We can just deal with 2 dimensions here. Yeah. And then so the library we're actually using for this is MediaPipe. And MediaPipe, this particular model is great because it was trained on more diverse data sets. Sometimes facial recognition has incredibly biased, as you might have all heard in the news. So it's important to start using a lot of these models that are a little bit more diverse and allow us to do better. So that's one of the reasons why we're using that one. Yeah, so then to get the landmarks, you just really need to run this line, and it draws over the frame like this. And now we have them all inside the bounding box. And so as I said, we've identified the sort of 68 landmarks. And in step 5, we have to take those, which include those XY coordinates that we were talking about just a second ago. And then we need to reduce that into some sort of embedding that then we can send to a model that will help us. So that embedding is called a descriptor. I like to call it an embedding because that's really what it is. It's just a vector. We take some, as we mentioned before, when we're talking about like the factory, we have to curate the data. We just transform numbers in some way, whether that's through some model or that's through our own, way of doing things. And then that makes life easier for us, especially when we want to do some sort of facial verification, because now we have an embedding. Now we can do the operations that are easier to do, like cosine similarity, which tells how similar two vectors are, right? Okay, so we do this. We have it stored in our vector database, and as I said before, these are the landmarks and identifiers. And yeah, so this is it. So what we can do now is that this is going to do k nearest neighbors. So it's going to do Euclidean distance, find out the neighbors around you, going through the database, and then find us the best neighbors and the distances. And then from there, we can select, oh, yeah, oh, I didn't, it's not showing the rest of the code. Well, and from there, we can select the winner. So what that does is that in this case, if you guys use the web app and put your name on the register, then you'll be in the database, which we will delete, and then your name would show up because once it does that search through embedding space, it finds the closest neighbor. Before I was some celebrity, but we can also change the tolerance so that there's some threshold as to how much we want to really say, make sure that this is the closest possible person within that the neighbors. So the web app is basically doing the same thing that we are doing with Python. The only difference is we're using Fast API to help us connect Python and JavaScript. And what we have Oh, another reason why we also use MediaPipe is not just because they are great at doing tons of stuff, like creating really great models and doing them more ethically. They also have really great library CDNs that we can use on the web. So that makes life a lot easier if we want to do a web app. We use MediaPipe's face mesh via CDN. And so that again is the one that creates a 3D sort of a landmark, but we're stripping it from all the extra information that it has to only 68 landmarks and two XY dimensions. What we then do is that we have it, okay, so then this is the Python. This is one of the endpoints. We have the face mesh thing every frame. Actually, I think I actually have the code for this. Yes. Okay, great. Yeah, okay. Um, so the HTML contains everything we always know, the CSS, style sheet, and some JavaScript files. We have the face mesh from MediaPipe. And then in the app.js, that's the one that engages with the front end, and it requests permission to use the camera because we always have to do that. Otherwise, I wouldn't really use browsers anymore. And then the MediaPipe will then get the landmarks for us and also the bounding box. And then we have to draw the bounding box because now we have relative landmarks in a relative space that we need to redraw on the canvas in absolute pixel space. And then once we have those landmarks, we send it to the Fast API, identify endpoint, and that's the same thing that was happening before in the Python code. Now we're just reusing those scripts. And then, yeah, and then we perform the transformation into the embedding space, which we can then use to search the database. Because again, the database is filled with people's faces that are in an embedding space. So it's again a vector. We have the landmarks, we have the XY positioning, we converted those into an embedding. That embedding is stored into a database for 5,000 whatever people, depending on the size of the database. We then have, again, I'm just repeating it just because I know it's like a lot of information. Then the webcam captures every frame. We're in the while loop. We're grabbing the facial features that it can detect. We have a bounding box. We have landmarks. We convert those landmarks through this model into an embedding. Now we have an embedding. Now we can search using this embedding what are other embeddings in the database that are closest to it using k-nearest neighbors. And based on the tolerance, we choose whether we want to verify, yes, this is Rolando, or no, we can't identify the person. So we won't go over the JavaScript code, so I'll skip like the first 3 steps. But here, this is the callback. So this is executed once MediaPipe has found the facial landmark. So we send those images to MediaPipe, the CDN, and then spits out some results. So in the results here, we have to get the width and the height, and then the important thing here actually is, I think like is like this loop where we go through all the landmarks and oh yeah. So remember how I said that we strip the huge information that MediaPipe gives us? That happens here. So we have that information already set, the 68 landmarks that we want. We map them, we extract them, and then over here, this is where, as I said, we turn it into absolute pixel space so that we can actually have it on the canvas. And then we get the bounding box. Yeah. The code is going to be online, so I know it's like really hard to process information. When I'm seeing at a talk, I'm looking at code. It's like, okay, yeah, but then also there's what yeah. So good thing it's online. And then yeah, and then over here, once we have the bounding box, yes. Okay. So then this is where we send it to the endpoint, the Fast API, and that's what ends up going through the Python code. And so then this is what we were doing, what I was describing. So we send it to identify. We have the landmarks, the bounding box. We package it into a JSON. We then send it through Fast API to Python to the endpoint identify, which has our scripts. We then have that response that tells us, oh, this is the landmark, this is this. We just make sure that it's a JSON because you never know, although it should be packaged as a JSON. And then after that, we yeah, and then after that, we have the data, and we make sure that we're able to display the name if we do find one. And sometimes, as I said, after we do that search through the vector database, we may not find a match. So in that case, we probably shouldn't say that it's like someone that it's not. Because again, if this was our actual verification system where we needed access to some door, we don't want the closest match if it's not a good match. Um, yeah. So then there is alternative methods. So yeah, this is one of those methods that's like model after model after model. And it's like, oh, do I really need to have all these models all the time? Well, not necessarily. There's other ways that you can do this, kind of like have one network kind of do it all. Um, and in that case, you would have to have some pre-training on the network where it tries to classify a face. It doesn't try to compare embeddings that represent facial features. And that's one way to do it. But the database way seems a little bit safer because you can have you might get more confidence from facial classification, but in embedding space, you are able to find you get a little bit more information. And that's how I feel. Um, and so a face classifier, again, remember how I said that this all looks super scary and complicated, but again, they're all just different architectures. We're curating whether we want to have 2 floors or an elevator in this factory that's going to help the workers do whatever they need to do based on the task. So I don't think I'll really go and describe this, but what really happens with convolutional neural networks here is that there's different parts of there's convolutions that are made and certain features get extracted, and then there's at some point where like we have like this really high dimensional embedding space that we do classification on top of a more fully connected layer to then determine, oh, this is Sue, Tom, Bob. But again, this means that we had to have trained on ground truth, which means we have to have trained on like all possible faces, and so we won't have access to that. So every time that we add something new to the database, we have to then train the network again on this. So it's better to just, if we need to do a lot of database stuff, we just keep adding people to the database. They're all in that same embedding space that represents the landmarks and the relative positions. And then we can do, again, Euclidean distances and other sort of vector operations to find the right person. So there's many things that we can do with this. I mean, we can classic home security. I don't know how many of you guys have like a home camera. Nope. Okay, so you have a home camera. Does it do one of the classification things where it tells you, oh, object or dog? Yeah, so now with this, guys could go, you maybe with a Raspberry Pi, attach a camera to it, and then you could start making your own security camera, maybe even a startup. Maybe you'll do it better. Um, there's obviously personalization. Obviously, one of like the biggest uses is for care and monitoring. So say you have an older relative, and it's nice to monitor them just because you don't know if they may have fallen, with babies as well. And then one of the most useful ones, and that there's actually already some repos that try to do this, but also like setting them up sometimes is a really pain in the ass. So I might just like go ahead and make my own, honestly, because one of the best things to do is actually uh, image organization for all the images that I've accumulated over my lifetime, which are a lot. I know there's like, maybe your phone service provider or Apple, if you use it, does this online, but sometimes I always feel a little bit weird having all that stuff online. So you can make your own cloud. Um, yeah, so I don't think I really have to do a quick recap because I was repetitive the whole time because I know it's a lot of information. And this is just sort of to give a little general overview of how that process might look like, how it might work. Um, but I think like the general, I think takeaway here is that one, neural networks are not scary. We don't really need to understand them fully to be able to use them. We're curators now. Then the next thing is that there is a very much simple way to sort of gather information. Say face detection might require bounding box. There might be a facial alignment. But I think like the next most important thing is having representations of input data is incredibly useful and an incredibly powerful way to think about how to organize and manipulate information. What is the best way to represent a bunch of material, a bunch of inputs, numbers that represent age or facial features, thinking about how we represent these and finding ways that this representation is useful for a particular task, I think it's like an interesting way to start thinking about problems. It's no longer can I get to A to B and then try a bunch of different paths. It's like, wait, is there some way that the path can be represented so I don't even have to do any sort of traveling? It's like a weird way to think, but I think it's like a really interesting one that's definitely helped me become a better coder. Um, yeah, and yeah. Anyways, the point is that there's many things that one can do. Facial recognition is one of them. Yesterday I talked about using AI to make music. There's a lot of ways that data has been represented. The music actually is also, oh, well, I won't talk about that now, but if you want to talk about it, like we can. Um, and yeah, so my brother and I, who wasn't here, that was kind enough to set up the server, were working on creating a lot of these sort of preset DIY sort of projects. Like this is one of them. The one for music was another one. There's one with stable diffusion where you learn to do tons of things, image to image. There's a lot of cool little projects that we're going to be working on. We're turning it into a book. So if you kind of just like kind of like going in and going straight into it, downloading the repos, starting to play, then you guys can keep your heads up for that. But anyways, thank you for your attention and time.
Quick disclaimer, if you have any questions, please ask them on this microphone so that the people who are watching this presentation online could hear it.
Hi, thank you for presentation, really great. I have a random question. So let's say I want to steal your identification, right? So I basically take your photo from this presentation and show it to the camera. And so I want to identify as you. Will your shown model will prevent that, or if not, how we can do that to prevent that? So basically, if I show the photo to the camera and I identify myself as you.
So this one would fail that test. Um, that's why it's sometimes better to use one that has more information, like XYZ. So include like that's why the MediaPipe they do the face mesh, which is a much better and much richer representation, and actually has like 468 features or something like that. And we reduce it down to 68. Makes it more efficient, faster, but you don't always have to do that. You can actually do a lot more. And this actually is an interesting question, right? How can you steal people's identity if you can just use an image? Um, and it actually reminds me of a very interesting study. This is kind of related, but it reminded me of that, where they did an experiment where in virtual reality, they had people watch a bunch of movies and they were just standing there. They were just standing, but you could like the headset has head tilt. The controllers also have, the gyroscope, so the XYZ and the rotation and all that. And then after that, after they collected a bunch of people, then were able to classify an individual just by the way that they tilted their head or that the way that they stood, because everybody has an idiosyncratic way of standing. So your question about facial of stealing information, that can be answered by just gathering more features, right? If you can steal my face, wait, what about the way you're walking or the way that you have your head tilted? That's not you because you never do that thing where you. But that means if we need more features, that means that we need to provide them. And that's another issue that comes up. Like, do we want to provide more information about ourselves and potentially reduce the privacy and agency that we have? It's an important question. Yeah.
Hello, I'm a bit hidden here, but maybe you can hear me at least. So
Oh.
it's kind of a follow-up question on the kind of identification theft and everything. So you probably know this that most smartphones have a facial camera, and some of them have also face recognition for face unlocking and everything.
LiDAR.
Yeah, and a lot of phones kind of skipped that part for a lot of authentication parts like banking and everything because it's unsecure. But just recently, Google's Pixel, Google Pixel 8, actually started using it for basically banking as well. And that would indicate that they think that only using camera to identify your face is enough. And my question is basically, do you think that only using camera to identify your face is enough to prevent identity theft, basically?
Oh, that's a really good question. Actually, I need to read up on this new system that they have. And now, is it one? Is it like, is it not dual authentication? It's only face? Wow, interesting. I'm not, it's a good question. The LiDAR provides a lot of information, right? There's like facial structure information. So you can move ahead from just like the facial features, like how separate your eyebrows are, to the depth of when your eyebrow starts from your nose. And it's really hard to change that about someone, right? So I see it being probably enough, but it's a little scary that it's only there's no extra step just in case, you know. But I mean, facial. I mean, everybody like our genetic code literally makes us all look different. We might know someone that looks a little similar to us, but we're all. This sounds so cheesy, but we are all incredibly unique, and but yeah, no, I think facial features is probably okay. The one thing that people failed at for a long time is like fingerprints. They thought that that was a good way to do things. It's really not. But I think that we can do that stuff now just because of like the mesh. We now have we're able to do some sort of 3D reconstruction of the face that has tons of features that reduce the probability of it being mismatched with someone else way, 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 way small. Small enough, I guess, that it's significant enough for them to think this is enough for security. But interesting, I'm gonna have to check that out. I have an Apple, so.
You used the landmark detection, and then you ran that convolutional neural network. What's the purpose of landmark detection? Then, if you already have identified the image of the face.
Yeah, that's another. Yeah, so exactly. There's many ways to do this. There could be one where you just send an image and it does everything for you. But there's different libraries that are better at different things. So I could have used a single library that does the landmark detection and then does everything for me. But MediaPipe allows me to do this web stuff. MediaPipe allows me to do really fast landmark detection. And so you start having to like focus on some trade-offs. Do I want to sacrifice a single model versus two because it's faster? Probably. Is it safer? To be tested.
Right. So it's just like more likely to identify the face.
Faster, like it's the landmark detection
you
is.
had one where you identify the face, that it's a face. Then you had the landmarks.
Yeah. Oh, so
Then you have the third one, which is the
the bounding box, as I said earlier, is not really necessary. That one's really just for fun. But there might be a model that you play with that does require the bounding box, and so it's there just in case at some point, you know, you don't have to worry about that. But the bounding box was for fun. You don't really need that. Not for this one.
Okay. Thank you.
Yeah.